Atmospheric CO2 is extremely diffuse at a concentration of only 400 parts per million. Recovering it directly from the atmosphere is known as direct air capture, DAC, and we've been carrying out research in this area for a long time. We're currently trying out a variety of DAC methods through trial and error, but at the start, we were skeptical about being able to concentrate the diffuse CO2. We thought it would require a huge amount of energy, even if we were successful. First, we needed a new sorbent material for capturing the CO2 at a concentration of only 400 parts per million. We used amine for this. We're currently on the verge of developing a new amine capable of releasing the CO2 at low temperatures. It can be used without heating, or heating only from sunlight or warm water. Making effective use of such heat will also require the development of technology for efficiently transferring that heat to the amine. CO2 capture will become achievable when we overcome these issues. This is a honeycombrotor dehumidifier. We ultimately want to develop something like this. We're carrying out initial experiments using supported amine that's commercially available. This rotor turns slowly at a speed of around 1 to 2 rotations per hour. First, we want to ascertain what's happening before and after air passes through it. On the front is the flow channel for recycling the heated air. On the back is the flow channel for sucking in air and absorbing the atmospheric CO2. This rotor turns slowly between these flow channels. It's just a conventional silica gel rotor coated with commercially available amine, so its performance is limited. If we use our newly developed amine on this, we should be able to concentrate the CO2 more, and that's what we're doing in our basic research. We're hoping to develop a process of converting the recovered CO2 into a liquid hydrocarbon fuel, like gasoline. This is known as FT synthesis, and it combines an endothermal reaction requiring heat with an exothermal reaction that releases heat. Conventional FT synthesis involves two separate processes, but we're trying to develop a membrane reactor that does both at the same time. This allows the generated heat to be used in the endothermal reaction. Excess heat can also be used in DAC, enabling any heat deficiency to be supplemented with waste heat or heat from the sun, boosting the efficiency of the overall system. Furthermore, setting up equipment that generates low-temperature waste heat next to DAC equipment will allow effective use of the heat. This will realize a system that utilizes waste heat on site in real time. We will turn directly captured atmospheric CO2 into a resource using a new amine, honeycombrotor, heat exchanger, and membrane reactor.
NEDO